this question is from GATE 2011 paper Civil Engineering. Question number 48. It is of 2 marks. A sand layer found at sea floor under 20-meter water depth is characterized with relative density 40%, maximum void ratio 1, minimum void ratio 0.5, and specific gravity of soil solids 2.67. Assume the specific gravity of seawater to be 1.03 and unit weight of fresh water to be 9.81 kilonewton per meter cube. What would be the effective stress rounded off to the nearest integer value of kPa? What would be the effective stress at 30-meter depth into the sand layer? So first let us note down the given data. So what are the given data? Water depth. Let us try to draw there is some water. This is the seabed. Okay, this is the seabed, and above seabed there is some water. Okay, that height of the water is 20 meter, and below that uh, relative density of this sand, which can be denoted by ID, is 40%, which can be written as 0.4. Maximum void ratio 1, minimum void ratio 0.5, and specific gravity of soil solids GS 2.67, specific gravity of the seawater 1.03, and gamma of fresh water 9.81 kilonewton per meter cube. Now we need to find out the effective stress at 30-meter depth. Let us say this point is P, depth is 30 meter. At this point we need to find out the effective stress. So this is the given data. Let me first sigma effective stress sigma P. It is total stress at P minus pore water pressure at P. Here pore water or pore fluid, you can say pore fluid, see UP is pore fluid pressure. Okay, pore fluid pressure. See, we used to use U as pore water pressure. Why? Because at the time the by default the pores of the soil used to contain water. By default the water means fresh water, but here especially that it is mentioned, it is seawater. It's not fresh water. So because of that, this UP is nothing but pore seawater pressure. Okay, pore seawater pressure. So pore seawater pressure is nothing but UP into gamma seawater into height. This is the calculation of the pore water pressure, where pore seawater pressure here it is. So now to find out this, we'll go to the diagram. First, let us calculate total water pressure separately. Total stress at P. So how is it coming? The total stress is coming due to the weight of this saturated soil and weight of this water. Okay, now how to calculate gamma saturated into this height? You can say this is H1, H2. Okay, gamma saturated into H1, H2, sorry, plus there is only seawater left above. So gamma seawater into H1. This is the total stress at P. So for that you need to find out gamma sat and gamma seawater. Whereas those two are not given, we have been given some other parameters. So now for this you can calculate ID. Relative density is written as E maximum minus, sorry, E maximum minus E divided by E maximum minus E minimum. So here E maximum is given as 1, E is not given, the in situ void ratio, and E maximum has given 1 and E minimum has given 0.5. So relative density is also given, that is 0.4. So 1 minus E by 1 minus 0.5 implies E equal to 0.8. This is the in situ void ratio. So you know the in situ void ratio now, and and you need to find out. Here we have been given gamma seawater as 1.03, right? 1.03. So what does that mean? Gamma seawater divided by gamma water. This is the formula for any specific gravity. Suppose here specific gravity of the seawater is equal to unit weight of the seawater divided by unit weight of the fresh water. So now what is the gamma seawater? 1.03 into 9.81. So that will be, let me calculate, that will be equal to 10.1043 kilonewton per meter cube gamma seawater. So this is another parameter which we need in the calculation. Okay, we know E, we know gamma seawater. Now let us find out what is gamma sat and what is gamma seawater. Okay, let us this let us give this equation as star equation. So how to find out gamma sat? Gamma sat, we know the formula from the relationships which are given in the second chapter of the book. G plus E into SR by 1 plus E into unit weight of the pore fluid, right? Pore fluid. So here G is specific gravity of the soil solids, that is given here 2.67 plus E we have found out, that is 0.8, multiplied by SR equal to 1 here because it is fully saturated we are finding. So SR is 100%, that means 1. So 1 plus again 0.8 multiplied by gamma pore fluid is nothing but gamma seawater. Okay, so this is how you have to find out gamma sat. So substituting this gamma seawater in place of gamma seawater, how much we have got? 10.1043. So let us complete this calculation. 10.1043 multiply it to this. So you will be getting gamma sat value 19.4788 kilonewton per meter cube, right? Then we know the H2 value. H2 value is how much? 30 meters. And now gamma seawater also we know. You know the H1 value, that is 20 meter. So let us find out sigma P equal to gamma sat into H2 plus gamma seawater into H1. Gamma sat 19.4788, 19.4788 into 20 plus gamma seawater is 10.1043 into, sorry, this is 30, this is 20. Let us find out. 786.4513, this kPa. This is total stress at P. Now we'll go to this. What is the formula for effective stress? One is sigma P minus sigma UP. UP is pore fluid pressure, pore seawater pressure here. Okay. Now I'll find out the second calculation is UP calculation, pore seawater pressure. So gamma seawater into height of the seawater, right, above the P. So above the P, what is the water height? Water is here also because it is fully saturated. So 50, total is 50. Gamma seawater is 10.1043 into 20 plus 30, 50 is 50 into 10.1043. This one is 505215 kPa, implies sigma dash P equal to sigma P minus UP 7864513 minus 786.4513 minus, so it is 281.23 kP effective stress at P. So let us move to the question. So effective stress at P at 30 meter depth we have calculated, that is 281.23. 281.23 is the answer. Okay, but which is the nearest integer? 281. So what is the answer here? Answer is D. Thank you.